Hi guys, welcome to the video tutorial for chapter 10.2 and 10.2.1 and 10.2.2. We've got three learning objectives that we're looking at. Our first learning objective is more or less a bit of a revision in chapter 10.2.1 and the new material is covered in 10.2.2. So roughly speaking, this is where the learning objectives are in the respective chapters. So if you feel confident in the first learning objective, feel free to fast forward straight into 10.2.2. All right, so we need to talk about graphing and calculating potentials in a uniform field. So again, just a straight recall of the formula for potential gravitational field potential, or voltage you might even say. And one of the first learning activities that I was hoping that you guys could do is to think about what were the electric potential formulas, okay? They should be quite similar to this one. Have a little think about that. Okay, so pause the video, think about that. Okay, welcome back. And so we're gonna have the electric potentials. So for a negative charge where it's going to attract other positive charges, this is going to be kq over r. And for a positive charge, it is going to be opposite in direction. Okay, so the voltages or the potential difference of those guys. Now, we're going to see this a little bit later is originally we talked about the derivation of G. Okay, so normally we're thinking of G from sort of like F equals to ma, came with a different derivation using the universal gravitation formula. Now we're going to look at another definition in the form of graphs. So in terms of a graph, it's the change of potential over the change of distance. So let's have a look at what that means. So here we have a potential difference. So potential difference here. So potential difference, or just potential maybe. So differences of potential, but each of them has a particular potential at that particular point versus a distance graph. So we should probably think of this as potential. And so at point A, the slope or the tangent, oh, did I erase that? Hold on. The tangent of this particular line right here, this tangent is the strength of the field. So you can calculate that as sort of like a rise over run, essentially, if you like. And here we have, we're taking another tangent. Oh, I keep erasing this. So if we take another tangent there, that is also the potential at that particular point. So two different values of G at two different points. So G1 and G2 is what we might call that, okay? All right, so now let's have a look at a quick example of what that might mean. So calculate the value on the magnitude of the gradient of gravitational potential at a height of 3,600 kilometers above the surface of the Earth. And we're given some information, additional information, about the Earth's mass and the radius of the Earth. So the first thing we're going to do is we want to find the total distance from the center. So to do that, we're going to take the radius of the Earth, 6378, and I'm going to just convert this into meters right now, plus the 3,600 kilometers, and we're going to get about 7,200. Okay, so if we went to two significant figures, we would have, oh, sorry, no, not 7,000, 4,200, right? 4,200 times 10 to the power of 3. So I guess you can even shorten that to 42 times 10 to the power of 6 meters. Okay, so next up, we're going to substitute in our modified sort of newly derived gravitational formula. And we got 6.67 times 10 to the minus 11. And our big mass, which is 6 times 10 to the power of 24, and our distance is going to be 42 times 10 to the power 6 squared. Okay, and so let's punch this into our calculator. 6.67 negative 11. 6 times 10 to the power of 24. Divide that by 42 times 10 to the power of 6. We got to square that. Okay, so we're looking at about 0.23, two significant figures here. And this is going to be meters per second squared. Okay, so you could do that as a form of acceleration. The field strength, another way to think about the field strength is it was meant to be a force per unit mass. So another way to express this is 0.23 newtons per kilogram, like that. Okay, so this was the basic definition of the field strength, force per unit mass, just like the field strength on the electrical charge is force per unit charge. All right, quick little review on the potential energy formulas for gravity and charges. So the only difference is the taking away of the square root of the distances, and we get energy, or potential energy. So second example here, we have a satellite with a mass of 1973 kilograms. It's orbiting the Earth at an altitude of 700 kilometers. And we want to calculate the potential energy of the satellite. So again, very similar calculations. We have the radius of the Earth, 6378 kilometers. 6378. I'm just going to convert that right away. Kilometers, that's now in meters. And it's 700 kilometers above the surface of the Earth, so 700 times 10 to the power of 3. So that's going to work out to 7,000 then, right? Yeah, 7,000, maybe 7,100 if you want to round it. So we have, sorry, we only got one significant figure, right? So 7,000. 7,000 times 10 to the power of 3, or you could say 7 times 10 to the power of 6 meters. Okay, next up are the potential energy of the satellite is going to be calculated using the formula that we had up here. So I've already copy and pasted that down. So again, we take the universal gravitation constant, look it up in your data booklet. The mass is 6 times 10 to the power of 24, if I remember correctly, kilograms. And the mass of the object is 1973 kilograms. And the distance is 7 times 10 to the power of 6. Okay, and if we work that out, just punch this into the calculator. 10 to the negative 11. 6 times 10 to the power of 24. 1973. Divide that by 7 times 10 to the power of 6. And we get about 1.1. So in terms of significant figures, our lowest value is, I mean, it's probably going to be 1, really. So, yeah, let's go with 1 significant figure then. Okay, so it's going to be 1 times 10 to the power of 11. Okay, and energy is going to be in joules. Okay, satellite falls to an altitude of 350 kilometers. So it's going from 700 kilometers to 350. Calculate the change of potential energy now, okay? So there is a difference in height, which means there's a change of the field or the potential. And now we need to find the change of energy as well. So very similar calculations. So we're just going to borrow this. And this is going to be 350 instead of 700. 350. And then so 350, that's going to be 30, 36, 37, 67? About 67 times 10 to the power of 3 meters. So I'm taking an extra significant figure because we got two significant figures there. So we should have two significant figures there. And we have 6.67. So again, same calculation. I'm going to copy and paste just to save some time. So we're going to grab this, copy, and paste that here. And the distance is different. So rather than 7, we have 6.7. And so we should have a slightly smaller number. And let me just punch this all in. 10 to the power of negative 11. 6 times, actually no, we have a, sorry, my brain's trying to do too many different things right now. We're going to have a larger number, a smaller number, times 1973. We're dividing by a smaller value. So we should have a larger value, divided by 6.7 times 10 to the power of 6. Okay, yeah, 1.2 almost. So this is 1.18 actually, if we were to round that off. So before we had I think it was 1.1, and now we have about 1.8. So almost 1.2. So initial energy is we had 1.1 times 10 to the power of 11. Oh, sorry, this is also 10 to the power of 11, not just 1.18. That would be a huge difference. 1.18 times 10 to the power of 11 joules. So I suppose we could round this off to 1.2 times 10 to the power of 11, as this has two significant figures. So first we had initial energy, 1 times 10 to the power of 11, minus 1.2 times 10 to the power of 11. So essentially it's 1 minus, let's see, my brain is just not wanting to work, so I'm just going to punch us into the calculator for everything here. So we should have a negative value, yeah, negative 2 times 10 to the power of 10. So we lost one power, and that makes sense as well. Okay, guys, so the last little bit also was suggest the effects of the change in altitude on the satellite speed. So if we assume that energy is conserved, then the potential energy means that there's going to be an increase in kinetic energy. So part of that potential is going to be converted into kinetic energy. All right, into our second learning objective is we're going to talk about satellites, orbits, and escape velocity. So relate the velocity of a satellite to its distance from the center of its planet. So we're going to do a quick little crash course on circular motion right now. And the real new or key thing you need to know about circular motion is that the acceleration, because it's no longer, we're not talking about linear motion anymore, or objects moving in a single direction, or in an XY direction. We're talking about an object moving in a circular fashion. So acceleration is now calculated as v squared over r. And so what we like to do with circular motion is we substitute this new acceleration into F equals to ma, and now we have a centripetal acceleration or centripetal force formula calculated as mass times the acceleration, and we're just substituting that as v squared over r. And so a quick little explanation about circular motion is that the force and the acceleration are always pointing towards the center. So if you imagine somebody swinging a, I guess something that's on the end of a rope. Let's say there's a ball attached on the end of a rope. Okay, so as we spin this object in circular motion, so there might be somebody holding onto this object, right? He's spinning this thing in circular motion. So the hand position, if the hand could remain stationary, is actually the force that's keeping this object in circular motion. So as soon as you release that object, it's going to go flying away, right? And it's no longer in circular motion. And that's why we talk about the force always being directed towards the center, okay, as the force necessary to hold or keep that object in circular motion. So that's how I have the word holding that object in circular motion. Now, what we're going to do when we're talking about objects orbiting around the Earth, now technically it's not a perfect circle, but it's easier to understand at this particular level of physics as a perfect circle. So what we're going to do is we're going to combine together the gravitational pull of the Earth as the object holding an object in circular motion, right? Gravity is pulling everything towards the center, very much like the hand is keeping that object from flying away. So we're just going to smash these two formulas together. And so I'm going to copy this. And this is now going to be equal to the other part of this, which I'm going to copy and paste. And then, so this does a few nice things here in the sense, whoops, oh, that didn't actually copy, did it? I guess I forgot to hit the copy button. Copy and paste. There we go. And then this allows us to cancel out some of these things, which is nice. So we can cancel a little mass. We can cancel one of the r's. Excuse me. And our latest formula is going to be v squared gm over r. And so if you square root both sides, you get the final version that is in your data booklet. Again, you don't need to know how to derive this necessarily, but this is sort of how we got to this point. Okay, now the relationship between velocity and the radius from the center is they are inversely proportional. Okay, now there is a square root over on top of the r, but it is an inverse relationship nonetheless, okay? It's just a little bit slower, you might say. So therefore, as an object moves further away, the velocity decreases, and vice versa, which means as an object moves closer towards the center of the Earth, the velocity is going to increase as well. Okay, example, the International Space Station orbits the Earth at an altitude of 400 kilometers. So altitude means from the surface of the Earth. Calculate the speed of the station. So I've just sort of fast forwarded because, again, we're just sort of repeating calculations. So the radius of the Earth, 6378, plus the altitude, 400 kilometers. And then so now we have our distance. And we just need to substitute that into our formula. Now, technically, this is probably supposed to be one significant figure. So that probably is going to be 7. So the one significant figure was determined because of that guy. So let's make our substitutions. So big G, 6.67 times 10 to the power of negative 11. And big mass is 6 times 10 to the power of 24. So I've more or less just memorized the mass of the Earth, which was a little bit earlier. You can go back to the video on that. And the radius this time is 7 times 10 to the power of 6. And then we need to square root that whole thing. So again, my brain doesn't really want to work right now, so I'm just gonna punch all of this into the calculator. 6.67 times 10 to the power of negative 11, 6 times 10 to the power of 24. Divide that by 7 times 10 to the power of 6. And then we need to square root our answer. Okay, so we have, so again, our smallest is, now technically this is about 7,500 meters per second. But if we had to sort of round that, we would have, I think that, I remember the rule here was that the number before was odd, so we round down, is it? So it rounds down to 7,000 meters per second, I think, is what will end up happening. Oops, sorry about that. Okay, sorry, where were we? Right there, okay, 7,000 meters per second. Okay, so let's head on to our third learning objective. So went through quite a few calculations. Last learning objective is to look at escape velocities from the planet. So there's a gravitational pull from the Earth holding an object in place. How do we escape that gravitational field? What's the velocity that we need to do that? So first off, this is going to seem a little bit strange because total energy is changing here. And total energy is changing the same way that potential energy is changing. Now, it's also important to keep in mind that these two graphs specifically, the kinetic energy and the total energy, are sort of, how do you say, they're opposites of each other, inverses of each other, is that the right term? But anyways, they're meant to be on the same amount and levels. Now, potential energy is actually the greater change of those guys. So it's important to remember though that the total energy is the addition of the kinetic and the potential energy. Okay, so it's certainly important to remember that that is the foundational definition of the kinetic and potential. So because of the way that potential and kinetic changes, the total energy ends up changing in relation to that as well. Okay, so let's see here. In order for an object to escape the gravitational pull of the Earth, its kinetic energy must be greater than the gravitational potential energy. Okay, so that's a given. So it can't be imbalanced. It has to be greater than that in order to have an escape velocity. Or we can think of it as the total energy must be greater than zero. So in terms of what it might look like as a formula, right, again, total energy is the sum of potential and kinetic. That's what we just talked about right now. And so if we add potential and kinetic energies together, so we're adding our two different formulas, this has to be greater than zero. So we're now working with this particular form, and we're rearranging the inequality. And so we're adding this on both sides, okay? And this also allows us to cancel out our little masses. And when you simplify everything, when you multiply the two, when you square root both sides, you end up with the escape velocity is the square root of 2 times g times big M over r. And this is found in your data booklet as well. Now there's an alternative form of this that you will find in Cognity. So I would encourage you to look at the other form of this particular formula. And actually, I'm just going to see if I can pull that up right now. It involves little g. And so I would encourage you to have a look at how they came up with that. And let me just scroll down here. So satellite velocities, the other form is, I'm looking for it. Okay, can't find it. Okay, sorry about that, guys. Okay, so anyways, we're going to keep going. Let's just go through this last calculation here, and maybe I'll talk about that next time. Example number 2, calculate the escape velocity on the surface of the Earth. So pretty straightforward, just straight plug and play here. We have 2 times big G, 6.67 times 10 to the minus 11, and the big mass is 6 times 10 to the power of 24, divided by the radius of the Earth. Was it like 6378 or something like that? 6378, yep. So 6378 times 10 to the power of 3, and then we need to square root that whole thing. Okay, so let's punch this into the calculator. 2 times 6.67, 67 times 10 to the power of negative 11, 6 times 10 to the power of 24. I should have probably just put this into memory. On my calculator, divide that by 6378 times 10 to the power of 3. Oh, hold on. My calculator went crazy. 6.67 10 to the power of negative 11. So I'm just repeating this calculation. Feel free to do this on your own. 6, 3, 7, 8. I'm just going to punch in the 3 zeros. Now we just square root the answer. Okay, so you have 11202. So in terms of significant figures, we're probably looking at 1 really, according to this. So it's going to be about 10,000 is what it will end up being. Okay, but that is of course the more accurate answer, but in terms of significant figures, we need to reduce that down to 1. Okay guys, that's it for this lesson, and I will probably see if I can dig up this other escape velocity formula that I have seen for you guys, all right? Okay, see you guys next time. Take care. Bye-bye.